organized by ICAMI UTPSC. The objective of this workshop is to enhance students' understanding on the fundamentals of software, which can be utilized in real-life applications. It is hoped that this workshop can reveal some tips and tricks that will benefit the students in their future projects and jobs. Thank you for your commitment and participation in this workshop. Next, I would like to briefly introduce our speaker for today's workshop, Mr. Zulfan Aziputra. He has more than 17 years of experience in process engineering and currently working as a process optimization engineer at ExxonMobil Malaysia. Now, without further ado, let us welcome the speaker today, Mr. Zulfan Aziputra.
Hi, good morning. Yeah, I want to make my background. How do I change my background? Yeah, sounds nice. Okay. Now, this is recorded, yeah, so I don't have to record it myself. Later on, you can please share the recording to me, yeah. I don't know. Please let me know if the internet connection from my end is not stable, or if there's some lag or whatnot. Just let me know, and then we can. And I have to move to a different room. But hopefully, I think it should be okay.
Hello, Mr. Zulfan.
Okay.
I think your voice is quite soft. I can't hear you.
Oh, is it now okay?
Not yet.
Not yet. Not yet. A minute. Now, is this now okay? Also no.
No.
1 minute. Now, is it now okay?
Yes.
Oh, okay.
It's clear.
Okay, thank you. Thanks. Let's do this interactively, yeah. Because it's going to be very boring if I speak alone, and then because the objective of this today's workshop is that it's a workshop, so that means by the end of these 3 hours, well, yeah, 3 hours sessions, you should be able to do something. But that's the goal. So in that sense, please just ask. And then please be active, because the only people that are going to benefit from this exercise is you, and you only. Okay, I will share my screen. Share screen. Share screen. Okay, bisa dilihat orang. Okay, so we'll discuss about symmetry first. And could you please remind me, you are all final year students or third year? Which one?
I think they are from various years.
Oh, okay. Well, okay. No problem. Let's just get started. Yeah. Now it's what time is it now? Okay, 15 minutes. Yeah, before we go into the how to use symmetry, I'll go briefly on some things that I would like to tell or share something about symmetry itself. We'll discuss on the process simulation. What is this? What is process simulation basically? Because some of you may know that already, some of you may not. So let's just set some ground basic. And then I will share something about what symmetry is, and then my own experience in using symmetry for industrial applications. Yeah, but this one, mind you, I've used symmetry for the last since 2016, so for last 6 years or so, 5-6 years. And then there are many other things that I've done before that year, when it was involving for simulation or modeling optimization, I used different software. So some of those applications I will not be sharing it here, because here we are discussing about symmetry, so it's not about process simulation in general. So before we go, resources, I think I need to share with you some of the resources that I've been frequently used. This is number one for you. So it's easy to read. I don't know if you know this, but if you know that already, so it's very good. If not, then this is for you to know. So chemical engineering design. So it gives you everything about the design, and also it gives you a glimpse on process simulation as well. This is the second book that is easy to read. It's all about design. And then this is if you go for a more advanced study. This is then the next step. So it gives you a more thorough explanations on process plan evaluations, design, and then simulation as well. So it all works based on simulation. And then this is another resources as well for you to help. And then this is some online resources that I think, so ChemN tutor and online ChemE, some learn ChemE thermodynamics, and this process design from Northwestern University. So it's this list is not exhausted, but then these are some of the best online resources that I could find until some time ago. So yeah, you could probably find another much better online sources as well. Okay, process simulation and its trend. There is this movie from I think from Cars 3, but you can watch it online from YouTube. Yeah, I'm not going to share with you. But the bottom line is that process modeling or modeling in general is that we make a simple representation of a complex reality. Yeah, again, so model is about simplifying reality, and then once we have the model, and then we can use that model to simulate what's going to happen if you have certain inputs that are different from what you currently have. Some of the process simulation software, we have Symmetry from Schlumberger, and there are other stuffs. Yeah, I think you know. So all models are wrong. So that means because it is just a simplification of a complex reality. So by definition, then all models are wrong. But what we need to know is then the trend. Yeah. So we need to know the prediction, what's going to be like. But in reality, how much is it going to be? It's quite difficult to accurately predict. But if we say, for example, if we open the valve over here, and then we shouldn't expect something somewhere there 5 kilometers away, what would happen in terms of the flow, of the pressure, of the temperature. So either it's going up or going down. So that should be something that we should be able to tell from the model that we built. Yeah. But if we say that I open the valve like 2 turns, and then you say that I can predict that the temperature at the end of the tunnel over there, it's like it's going to be increasing by 20.3 degrees C. That's not something that you can tell. It's just it's not possible unless if you spend an enormous amount of time to really make a very accurate model from this particular valve to that particular end, and that's probably then you can do it. But in most cases, we cannot do so. So why do we do process simulation? There are several things that why I do process simulation. Yeah, the most common one for you and also for us chemical engineers. Number one, we use the process modeling or process simulation software to calculate mass and energy balance. So from this mass and energy balance, we can do all sorts of things. Number one, primarily, is then to do equipment sizing. So we size the equipment. So we not from that mass and energy balance, we have several cases, and then we can then size how big is the pump, how big is the exchanger, how big is the vessels and reactors, and so on and so forth. And then typically, once we have that mass and energy balance model, we can use that model to find some root cause of a problem. Say, for example, you're saying that I'm giving this input as much as I can, but I don't get the output as expected. So from that model, you make the model of your plant, and then you can see why is this not behaving as expected. So then maybe you can see there is some losses somewhere, which you can quickly identify once you have the mass and energy balance model. If you don't, that means you have to work really hard to walk around the plants, ask the operators, get some data, and then find if there is any losses. But that's one thing why what we can use process simulation model for. And then once we know that, then obviously we can then improve the performance. So we can increase the yield, we can minimize the losses by tweaking some of the valves on the plant. And then how do we know that? And then we could also then we can see that by doing some sensitivity analysis on the model itself. So say, for example, I increase the flow rate, I increase the duty, or reduce some pressure, and then you might see something. You could also use like a dynamic simulation model. So this is one step further. We learn this typically during our process control class. So if you pay attention to your process control class, you should be modeling the whole class in the dynamic mode. Yeah, in dynamic mode, because then by using that dynamic simulation, you could evaluate the control system and also the process safety related issues as well. And then coming back to the steady state process simulation, like what we have done for the mass and energy balance, we do like a techno-economic analysis for different new processes, different raw materials, catalytic systems, and so on and so forth. And then if we, during that study, if we find that some part of the process it takes, it's very expensive to do. So that means we need to be able to find a new way to minimize that cost. So that finding a new way to minimize that cost is what we call like a future research direction. So if we want to go one step further on the research, then we need to tackle the biggest issues. So one of the biggest issues that we could tackle is definitely reducing the cost. And then obviously we along the way we modify and debottleneck the plants of the process and so on and so forth. But these are the things that I've used process simulations for the last more than a decade or so. But basically what I've been telling students or young graduates or even engineers, all engineers, is that if you happen to work in a plant or you happen to have different problems related to the industrial plants, just make your mass and energy balance, even though no one is telling you to do so. But for you now, I'm telling you to do so. Just make mass and energy balance so that number one, you understand your plant or your process perfectly. Number two is that you could identify all of these problems. So if you could identify all the problems, and then you can then make some priority list of modifications or adjustments. And then you can then show this to your boss, and then it will then show to them that you are a proactive engineer. So you deserve to be listened to, and then they will then give you an opportunity to prove yourself. So it's there's much going on for you. Okay, just make an mass energy balance for of your plants. It's not that easy at the beginning, yeah, especially for your during your first 5 years or so. Not going to be that easy. But if you have done dozens of this mass energy balance for every plants that you visit, you'll have some wonderful skills, I would say. The current trend nowadays in process simulation is not what we call, I mentioned here, first principle model. So first principle. So first principle is then what you call, what you have learned so far in the 4 years of chemical engineering program. So if you know that PV equals to nRT, that's what we call first principle. Q equals to MCP delta T, UA delta T, LMTD, and then MPV, and so on and so forth. So all of these equations, these are all what we call first principle modeling. Yeah, but many of the situations in real life, there are things that we don't know, obviously. Number one, because there is no measurement, we don't measure it. Number two, even if we measure it, the measurements are wrong. Number three, simply that we don't understand how the mechanisms work. So because of these issues, as long as we have a data, we can find a work around it. We can find a work around it. So one workaround is to make like a regression model. So this regression model can be in the form of linear regression, nonlinear regression, neural network, or decision tree based. So these are the things that you may or may not have heard, but just bear with me. So when we combine that regression model and with the first principle model, that's what we call like a hybrid modeling. So this is then the current trend. It started like last year, 2021. Yeah, from both of the companies. If you know Aspen Tech, and then if you know Schlumberger. So from these two companies, they released the products which they claim able to do this hybrid modeling. But I will show you how. I mean, we'll just show you a glimpse how we could do it in Symmetry, but we cannot do it in Aspen, even though I don't know what they claim. Okay. Yeah, this machine learning model, let's go quickly. Yeah. So if we have a data, so it's either from your plants or whatnot, from your literature, and then you can make, if you have enough data, you can make your machine learning models, and then, or you can also make your process simulation models for the first principle, and then some properties or data can be transferred in between. Yeah. For example, if we have a data on the reducing, if there's a heat exchanger, for example, heat exchanger, and if you are reducing the temperature values, and then you can then predict with this machine learning model what is then the overall heat transfer coefficient, for example, as a function of T, and then you can then put that number into process simulation model. So you could do that, or the other way around. So for example, if you have data, and then you can then use the data to calculate the overall heat transfer coefficient, and then you can use that to build this model. And then yeah, either this or that, you can then use them, or both of them, you can use them to make a decision. This is what I mentioned. So this is what what's in the hybrid model in unit operations capable of handling neural network model, and that one as well. So it is there. Yeah, and then it is integrated with typical first principle. Like we have a flash, we have pumps, heat exchangers, and so on and so forth. Now symmetry. What is symmetry? If you know HiSys, so Hypertech of Hypertech, so the same founding fathers with Symmetry, but Symmetry is using Microsoft Visio. Yeah, so if you know how to use HiSys, and then you could then know how to use Symmetry without knowing it. It's just that visually it looks more beautiful, you know, because it's has this Visio and stuff. It's now under Schlumberger. So it's if you have now, because they are now, this product is now streamlined, yeah, with the other Schlumberger products. So you can then make a model from your reservoir to the well to the topside pressure, topside facilities, and then up to your onshore facilities, up until the flare. So you could basically model the whole facilities from the ground up until you dispose it. So you can do so theoretically. Yeah, practically that's a different story. And then they have like a more elaborate thermodynamic models, especially from compared to HiSys, because HiSys it stops the thermodynamic modeling development when they are bought by AspenTech. So and it's continuously updated. So you could model more and more systems using Symmetry as opposed to HiSys. But in Aspen Plus, it's because it's Aspen Plus is more like a calculator to me. So you could even make all kinds of models in Aspen Plus as long as you know how to do so. Okay, but it's not as user friendly as HiSys of Symmetry to use it. And then it also contains more optimization solvers compared to the HiSys and Aspen Plus. And then, like I mentioned, it has this machine learning feature in it, which I couldn't find it in the other software as well. Well, in the end, all of these are tools. Yeah, in the end, all of these are tools. Whether you use calculator, Symmetry, HiSys, or whatnot. Well, in the end, what matters is then you. you are the person behind the gun. So you use it, so you should be able to, you should be responsible on the results, on the everything around it. So if you are no good, and then there is no good in using any of this solver or software. So what I like and I don't like, there are a few things. Yeah, I think I will go quickly on this. Thermodynamics, as I mentioned, in Visio, open platform for machine learning model, and then robust neural network deployment. So it's related to the machine learning model, and then it's a for sheet convergence window, so we can prioritize the recycling loop. And then the user interface is a clean, straightforward, and then you can use the same flow sheet to make a steady state and then also dynamic model, just like HYSYS, but we cannot do so in Aspen Plus. So in Aspen Plus, it has to be like we export that steady state model, and then we open that steady state model, the exported steady state model from Aspen Dynamic, and then we can fine tune. So it's not that easy transition. A lot of optimization solvers, many options for pressure drop correlations as well. Then context can be easily configured, so just like HYSYS. But what I don't like about this is that, like I mentioned, I like Aspen Plus thermodynamics model much more. But so now there is no shortcut distillation unit. I think in Aspen, HYSYS or Aspen Plus, you have the shortcut distillation unit, but not in Symmetry. And then the development of our own unit operation is not as straightforward as in the Aspen custom modeler. So we can make our own operating unit in Symmetry, but it is not that as straightforward as Aspen custom modeler in Aspen Plus. Some chemical industries features, because historically Symmetry, just like HYSYS, were developed for to facilitate to serve the oil and gas industries. So things like residue curve map, ternary diagram, isotope finder, which we can find easily in Aspen Plus, these are not available in Symmetry. And then it also requires extra costs like pipe network solver, communication tools like OPC and so on. So we need to pay a lot more for that. But you guys in the universities, well, you don't need to pay for anything. And there is bugs in pinch analysis tools, and then help is also not so helpful, I would say. But anyhow. Some features we can see it directly. Industrial applications, I'm not really sure if I want to do that, but let's spend another 5 minutes on this, just to give you especially for those of you who don't know what process simulation is. So just to give you an idea, so I've done all of this using process simulation or process software, but the ones that I've used Symmetry in it is then the application is in oil and gas industries, safety, and then artificial intelligence and machine learning. So just go quickly. The rest I've done it, but it's I used a different software for that. I think we are somewhere here in the Selangor, right? And then this is Malaysian Peninsula, and then these are all dozens of oil and gas platforms or wells. And then they are all connected with pipelines, and then these are all like hundreds of kilometers away. And then they are commingled somewhere in between. Also, they commingled somewhere in here in Krete. I don't know if any of you has passed by this area. Those of you from Kelantan or Terengganu, you may have seen this part of the world. So we make a model of these pipelines. This then sketch the schematic and then how the model looks like in some of these pipes here. So we have two. In this case, we have two wells, and then so this well is sending, in this case, gas, liquid, and water. Primarily gas. And then these are the pipes, and then they're connected over here, and then it sends to this what we call like a slug catcher or receiver or whatnot. So this one can be here or can be there depending on where you are. And then from here, the slug catcher, it catches slugs, so it removes the liquid, which is then the oil and water, and send it here, and then the gas is then sent over there. We have like a monthly data, and then we fine tune the model in such a way we see that whether it matches the data. So you can see it matches the data, and that means this model is good to go. So we could use it, but then the only how do you call it? So because they need the model to see whether if one of the wells is shut down or if there is any problem with one of the wells as well, then we can expect the impact. We can expect the impact. We know when we can expect that impact because this is dynamic model. So if it dies now, so can we see the effect like this afternoon or tomorrow or the day after tomorrow? So using this model, we can see that that prediction. This is also another video, but I will skip this. This is another example. I will skip this, and then this is for the safety. So if you know a distillation columns like this, so it has like a 3 reboilers. Yeah, in your class you learn like the distillation column has a reboiler, but practically you can have like tens of reboilers, and then it is connected to also to a condenser and then reflux drum, and then this then the distillate stream. This is then the reflux stream. We model these systems. It has these 5 process safety valve in it. So we model all of these systems into this kind of model. So we have the input line over here. We have different types of trays. Hence, we have 1, 2, 3 below over here, and then 1 on top of that somewhere here. And then we have like a 5 process safety valve, and then this then the reflux drum. So we have the reflux over here. Sorry, the distillate over here, and then the reflux over there, and then the reboiler is in here. Yeah. So I make the 3 reboilers in this process calculator so that I can switch on, switch off whichever reboiler that I need to. So in this case, for example, say if this condenser fails, so this dotted line, so it fails, so there's no more value, 0. So if this fails, that means all of this vapor is not going to be condensed. Yeah. So we have it's going to be pressurized over here. So if this pressure is increasing, that means this pressure is also increasing because they are all connected. So if the pressure here is increasing until a certain set point, this valve will open. So you can see the pressure is then going up until the 21.5. So there's then the set point, set pressure where the PSV is popping up. So it needs about 9-10 minutes to do so. So that's the results. So once it pops up, so all of the gas is going to be released to the flare. So we see that the reductions of the pressure like that. Okay. Now I'll show you some stuff. This one, yeah, the rest is about the same, but I would like to show you this one. So in this case, we have how we deploy or implement the neural network model in Symmetry. So we have, for example, we have like a pipelines, and then and in multi-phase flow like this, we have gas, liquid, water. Liquid means oil, yeah, oil, water, and then also we have also sand. So this sand, it can erode the pipe. So we do like a CFD modeling to see where that sand is going to erode the pipe. So obviously somewhere in the band, and then from that band, from this simulation, we can calculate how much is then the erosion rate. So in this particular example, it's about 19.6 milligram per square meter second. This neural network, we connect them to the Symmetry like this, so we can then calculate what is then the erosion rate, and then this unit we can then plug it in to the process simulation software in such a way that we can see if we play around with the velocity of liquid, gas, and then the liquid and gas, basically, because we can basically you can control this a little bit. So in such a way that we can then see the effect on the erosion rate, and then we can then minimize this. So that's how it is done. Okay. This is another plant. So this plant is the original plant, and then I compress them all into one machine learning unit operation. Okay, so we can see that the error between these two is very small. So which we can say safely that this model behaves exactly like these guys. So instead of having these big models, and we have many recycles, and then the problems of convergence, so we could then deploy this model so that the operators can see what is going to happen if they change one of the inputs. Like this, we have 5 inputs. So if they change one of the inputs, instead of running the simulations, which may or may not converge, they could simply run this, and then it will then always converge, and then it will then see the effect. Okay. I'll skip this. Yeah. Now, we have yeah, 2 hours or more, and then I will leave another half an hour for questions and answer. Um, do you all have access to Symmetry? Are you opening now Symmetry? Are you opening Symmetry or are you not opening Symmetry? No question. No, sorry, no question. No answer. Hello, hello. You have your Symmetry now. Okay, at least I have one. You open your Symmetry, yeah, like this, and then you will see a window like this, right? Okay. Yes or no?
Yes.
So I assume it's yes. If not, then well, again, like I mentioned, this workshop is for you. It's not for me. I could I can use this with my eyes closed, but it's very important that you can then follow along, because I don't want you to at 12 o'clock noon and then you come out of this session and then not knowing anything or whatnot on how to use Symmetry. That's what I don't want you to experience. So I want you to have a good experience, so that in a way, after 12 o'clock this afternoon, then you can confidently use Symmetry for your. So we could yeah, like create new case. So that's what we do. Yeah, it has to be active participation. Yeah, you need to tell me. Typically when we click a new case, we'll have this kind of window. Automatically it comes from this button, thermodynamic model. So it's basically the place where we select our own thermodynamic model. So in this all thermodynamic models, in this thermodynamic tab, so we have this thermodynamic tabs, compounds tabs and settings tab. And then in this thermodynamic models tab, we can then so all kinds of models. So you can see there's a long list, and then in all of this is also a long list of thermodynamics model that you could use for your own specific cases. And then from this thermodynamic model, for example, because I received an let's do this here. I received from your colleague Li Jing, because I asked him what kind of case that you would like to do. So this one. It's about cooling medium steam power station. So we have steam, which is basically water, right? And then is there any other stuff? Water. So there's no. So we'll do water, and then air, and then the 134A R. So we'll see. So let's add water, and then this is a steam cycle. So in this particular case, your thermodynamic model is the thermodynamic model of water. So you could you can see to steam tables. Pick the latest one, the SME 97. Okay, SME 97. And then the compounds is basically water. So you could either type and then press the button once and then press it again, it will be selected. Or you could also like water and then a double click on this, highlight it, double click, and then you get, no, I click too much. And then you can get water, double click, one click. So you can get water in it. And then the name of your thermodynamic model is then VMG thermo, so you could name it like yeah, your model. So your model is then your model, and then it's using Steam 90 dynamic model. Okay, up until here, is it clear or not clear? Can you follow? Can you follow or not?
Yes.
Good. And then you click done. Yeah, if you don't want to talk, it's also fine. Just say yes or no. Okay, now we have the thermodynamic model. We know how to select thermodynamic model. We know how to select the components that we need, and then the next step is then the unit sets. So we need to like yeah, depending on which unit that you are familiar with. So here we in more familiar with SI units, so that's the units that we're going to use. And then the last thing before we go to this palette, I will show you how to find a help file. So it goes here, help, and then symmetry manual. So for everything that you don't know or you want to know, it's here. Once you collect that help file, yeah, once you collect that help file, and then pop. So this guy will pop up. It's basically in your installation folder. C program files, PMG, symmetry, documentation, symmetry, user manual. So that's basically what it is. So you can search, for example, I don't know. So there are many things, fundamentals, process modeling, flare, and so on and so forth. Say, for example, you want to find something like a valve, I don't know. So this valve is, there are 99 results. So you can go valve. When you click this valve, is over here under the valve directory, and this is under piping and flow, under unit operation, and the pipe modeling as well. Yeah, so you can see there are like the general information about the valve, and then example on how to use that valve. And then here, if you want to go for dynamic modeling of that particular valve. Okay. So the same way, if you search for other stuff, yeah. So I'm now showing you how to do that. So at least then you can go ahead and then find your way around this. So that's all done. Thermodynamic, one more thing about thermodynamics. So say for example you miss one component, and then okay, now how do I get back? So you can simply click on this thermo, and then you will see the same window, and then you have your water. So now if for example you want to add some air, we have air, no air. So we need to have like oxygen and thing like that. Okay, and then you click done. Now say for example you have just make a material stream, yeah. So it's because this is VCO basically, so it's just a matter of drag and drop, like you use VCO normally. That something like this. So if it's like a yellow and it's dotted, that means this is not solved. So we need some more information. See, not solved. If you hover over it and then double click, when you double click on it, and then you can see. So my laptop is very slow. Okay. So now here you can name it as you want here. Your stream, my stream. So you can name it, and then here we have the composition. So in this case, maybe we can want to have like a water only. So one, and the window pops up, and then you can see it's small composition. It's small on composition, right? And then I want to simply enter, and then you click OK. For example, you have another 0.01 over here, so and then this then 0.03 over there, and then you can see that this is above 1. So it's not possible to have a total of more than 100%. So in this case, if you say, well, this is also true, so you could do normalize. It will then be normalized according to these numbers, yeah. But the total will be like 100%. So if you click normalize, something like that. So you have like instead of 1, you have water like 0.96, and then oxygen 0.09, and then nitrogen is 0.0288, something like that. Okay. So if you click OK, and then you will see this composition, and can calculate the phase of that fluid. Yeah. So this is what we call like there are three items that we need to specify before we can calculate them. Yeah. So them means the temperature, pressure, and then the vapor fractions or the phase of the fluid. So in this particular case, with this composition, these conditions, your vapor fractions is 0.04. So basically, you have like a 4% of vapor, and then the rest is liquid. So in this case, you can see your vapor is coming from these gases. Yeah, your vapor is coming from these gases. And then now, why you need 2 out of 3? Why do you specify 2 out of 3? Why not 3 out of 3 or 1 out of 3? So that is something that you have to ask your thermodynamic lecturer. So if you don't want to ask it, then you have to go back to your thermodynamic book. So if you ask me to explain this, it will take another 5 minutes. So we could do so later on. So now, say for example, I want to have like a 1 tons, I don't know. And then so once we press this 1 ton, include this 1 ton, the whole thing is solved. So solve green, and then we have all the informations available for us. And then you can click the properties, the drop down, and you can see the energy is that much, the enthalpy is that much, the entropy is that much. So all of these are compared to the baseline. So I don't know what the baseline that they're using, but nonetheless it is there. Molecular mass is about 18. It's not 18 because you have oxygen and nitrogen in it, so it's not perfectly 18 like for water. And you have the density, and then Cp and so on and so forth. So this density is about 18 or so. So why is this 18? Because it's very light. Yeah, if you have density of water is 1000, so this density it could be because of this vapor coming into it. So it will then lift up the water a little bit. So it makes the density of the water that low. But I'm not really sure if this number is a correct number. But nonetheless, this is very small because there is the presence of this oxygen and nitrogen. So if you remove this, for example, I want to have like 1. So you have 1, and then your density is exactly 997. Okay, see? So if you put another another gas, and then you will have a lower density, and then you can see if it's like a pure water at ambient conditions, it is water, it is liquid, sorry, it is a liquid. So there is no vapor, so it's all liquid. Okay. And then you can see that the color changes. It was blue, now it's a purple. So what it means is that you can go to tools and then settings, and then you go to Visio PFD, and then you can see here. So if it's purple, it's a liquid, which is what we have now. And then if it's blue, what we had before, we have like a liquid and an air, right? So it's a mixed phase. So it's blue, and then if we have like a full vapor, we have teal color like this. So you could change it, but I will just leave it like that. So it's not something to memorize, but it gives you an indication that the phase may change already. So it is a help in this regard. Do you have any questions so far? No? Okay. If you don't, then fine. So I will put it here. Just close this. I will show you. Let's see if we can do this quickly. I'll put it side by side so that you can see it and I can see it. So small. Okay, can I do this? Okay, now. Yeah. So this steam turbine stuff, let's read this together. So in which the electric generator is steam driven and then uses heat energy generated from burning the fossil fuels to produce electrical energy. So it's very inefficient, yeah, from that perspective. This type of power station is widely used around the world simply because at the time people don't know any better, and then nowadays people know something better, but because it has been historically done that way, so people are reluctant to change. Nonetheless, it's operated based on the Rankine cycle. So what is the Rankine cycle? What's Rankine cycle? So if you don't know, then you can Google this Rankine. Or if anybody you know, is there anybody on the audience know what Rankine cycle is? So Rankine cycle is, where's that stuff? This one. So we have which one is the easier? Rankine cycle. Oh, find picture. Nah, this one. So you have this. So you have it says you have a boiler and then you are burning fossil fuel, right? So you are burning fossil fuels, and then from that fossil fuels burning, you make your steam. So see, steam is produced in the boiler. So you have a boiler, and then you are using fossil fuels in it, and then you burn it. The question is that well, we could model this, yeah. We could model the fossil fuel, the amount. Just do that. Just for the sake of introduction, yeah. So now we have a fossil fuels. So what kind of fossil fuels that you are using? What they're using, it's not known. Nonetheless, well, let's just use methane gas. So in that methane gas, say for example, we have we forgot to put methane, right? So we add methane, methane there. Click once, so you have your methane. So we burn methane. When we burn methane, we need also oxygen. We have oxygen, and then we have water, and then we need also CO2. Right. So now, so you have your methane, for example. Now your natural gas, and then this is like assume it's like pure methane, right? And then it's I don't know, it's ambient maybe, and then it's just simply slightly above atmospheric, because then you can then push it towards the burner. So let's make it like a 2 bar, 2, and then you can, because this is the unit is then in kilopascal. So if you put 2 bar, so you want to change it to bar, so you can either put 200 kilopascal, or you can just simply press space, and then you have press space, and then you have all kinds of units over here, which you can then select from. So 2 bar, which is then 200 kilopascal. So you can also make like, I don't know, 1000. Just put like a nice number. Okay. So you have methane is 16 with mass density is very close to air. So it's just slightly above air. Okay, so now we have natural gas, and you want to burn it in the furnace, right? So to burn it, you need to have like oxygen. You have oxygen, air. It's also like 25 degrees C. It's like a normal air, and then it's also like 200 kilopascal. And then you could then see now oxygen is 21%, and nitrogen is 79%. So if you don't know these numbers, you can also quickly Google that. Yeah, click OK, and then you could also then say, okay, now it's 1000. Just put some number. So these are, I forget to mention to you. So all of these bolts, things that are bolts, these are things that we select, that we input, yeah, that we input. So this is what we call like a degree of freedom for this calculation. So the non-bolt ones, these are calculated numbers, so you cannot change or alter. but the ones that in bold, you can change it. Okay, so you have now air, you have nitrogen and nitrogen, you have natural gas. So you burn it because you need to have that heat. You need to get that heat from the burner. So how to do that? So obviously, number one, you have to mix them, right? So you cannot react something because it's oxidation reactions. Just drag and drop the mixer, connect it over here, and then this one is over there. And then you can see it was gray. Now it's a dark black. It means it is solved already. See, it's solved already. Why it is solved? Because we haven't specified anything. It's simply because there is one degree of freedom for this mixer, and it's just calculates the outlet pressure over here as the lowest between the inlets. So we have now two inlets, air and nitrogen. Air and natural gas. So the lowest pressure of the two becomes the pressure over here. So this is then in zero. In zero is the air over here, which is air. So this is quite inconsistent. So this is also what I don't like about symmetry, because air is on the top, air is on the very left, and then I would expect that air is also on the top, not the bottom, but nonetheless it is there. So we have natural gas, and the second inlet, both are 200 kilopascals. So this is also 200 kilopascals then, and then they are mixed together. So it's a simply mass balancing. Simply mass balance. You could see as well, the mass is just 1,000 plus 1,000, 2,000, and then the energy also, it will then be calculated accordingly. Okay, so in this case, you can see out is over here. So for this, if you click this anchor, keep window on top. So that means if you click on that, I mean if you click anywhere on the flow sheet, this window stays on top. So out is somewhere on the right side. So over here for every unit operations, and then in is somewhere on the left side like this. Yeah, the same goes with the, we have in stream over here and then out stream over there. Okay, so and then that's how they calculate this block. So it will be calculating block by block from getting information from the inlet input over here, and then it will then calculate what's the output, just like this one. So we can simply, because the output has already been calculated, we can just simply drag and drop this stream over there, and you can see this S1 is connected, and then it is solved automatically. Okay. Yeah. So now we have the mixed air with the we mix the air and then the natural gas, and now we simply burn it. So that burning is an oxidation reaction, right? So that oxidation reaction, so if we assume it's a complete combustion, because what we care more is on the heat that we're going to extract from it. So we can go to reactor. Reactor is, yeah, you can simply just get a conversion reactor like that, and then connect it there, and then double click on that. So from here we have to define, so it's a conversion reactor, so we have to define the reaction first. So this is oxidation reaction. So now we can go to the reaction tab and then click add or edit, and then you can name it oxidation reaction. And then you can say it's methane, right? So methane is it's -1. So methane has 1C, so it means the carbon dioxide will also be 1. Could also be 1. And then we have we burn it with O2. So CH4 plus O2 becomes CO2 plus H2O. So how much is that DH? How much is DH? Huh? Hello, hello. Hello. How much is DH? So it also means you need only 2 water. So 2 water needed. So you have a CH4 plus O2 becomes H2O plus CO2. So you have 4 oxygen on the right hand side. So that means on the left hand side you need to have another 2. So when you do so, you see that this balance becomes 0. If this is not 0, that means the stoichiometric stoichiometric reaction. Okay. The conversion is 100%, so assume this to be like 100%, 100. And then so what is then being converted? So this is then what this base component is all about. So we need to specify. We have specified the reaction. Yeah, we have specified the reactions. We have specified the conversions. What we haven't specified yet, what is being converted. So in this case, what is being converted to 100%? What is being converted by 100% is then the methane. So in this case, we put methane. Okay. Minus, you know, minus means, yeah, minus means it's on the reactant side, plus is then on the product side. So this is then the conversions, and then this is then the heat of reactions at 25 degrees C, 802 kilojoule per kilomole. Sorry, megajoule per kilomole, 102 megajoule per kilomole. And then you click OK. There's no other reaction, right? If there's more reactions, then you can just click a new. Okay, so now we have the reactions. Now up until here, do you have any questions, or can you follow this? I don't know. I know that I'm maybe too fast, but I'm not sure. Can you follow?
I have one question.
Yes.
Can you open the reaction tab again? So how do we decide the base component? Is it something like limiting reactant, or how do you decide it is a
What is
methane?
being reacted? What's being
The
reacted?
base component.
Oh,
So the reactant. But I think we have two reactants, right? Methane and also oxygen.
So yeah, so in this case, what exactly that you want to do with these reactions? You want to because oxygen is an oxidizer, so it will oxidize something. Yeah, but you cannot methanize. You cannot methanize oxygen. There is no such thing. So if you oxidize methane, so that means that methane is a base component. Obviously, mathematically speaking, you could then use oxygen as a base component. It doesn't really matter as long as it is one of the reactants. Yeah, you could do so. But then from the physical standpoint, something is one that is being limited. So that's a limited thing. So that is then the methane. Methane is being oxidized. That means methane is then the base component, or methane
So I think your connection is not quite stable because I can't hear you.
Is it okay now? Hello?
I think it's okay now.
Hello?
Yes.
Can you hear me now?
Yes, I can hear
Can
you
you or
now.
can you not? Hello, hello.
Hello, can you hear me?
Yeah. Can I do ya? Oh. Hello? You cannot hear me, yeah? I will
Yes, I can
disconnect
hear
and
you
connect
now.
it again. I will do so. Hello?
Hello.
Hello, can you hear me? No?
Yes, yes, I can hear you.
Okay. So when did you lose me? Um, um, so what was it? Yeah. So when did you lose me? So I was we were discussing about how to use the base component, and then I said that the base component is then the component that is important in the reaction, or the ones that is then in this case the one that is being oxidized, which then the methane, which is then the main component in this particular reactions. Is that clear, or do you need another example on on how to select the base
Yes,
component?
I think it's clear.
Okay. Okay.
And also we have another question from the audience in the chat box.
Mhm.
He asked, can we add catalyst-based reaction into symmetry?
Yes, why not?
That's,
Yeah. The question is, if you can we or can we not? Yes. The question is then how can we understand what is being done? So in this particular case, for example, in combustion reactions or in other reactions, so there are there are several things to consider. Yeah, there are several things to consider. I think that stems from the understanding of reactions engineering. Basically, it's not about the tool. So now, let's see if I can write this. So now you have component A, and then reactions, and then this is then A becomes B, and this B, and then you can say now, well, I have a catalyst over here, and then during this period of the catalytic reactions, I make B from A. So now question number one is then how much is then B being produced? So if you know that, well, the yield of B is then 90%. So that means you can simply calculate B, right? So you get your B. B is done. So and then you can come back with your reaction engineering class to say, okay, so if I want to have B 90%, I know this information from the literature, and then I know how much is then the flow rate of this guy, and then you can then calculate how much is in the volume. If you know the volume, right, you can calculate the volume, and then obviously if you know the volumetric flow rate over here, and then the density of this guy, or you can have a mixture of density, and then you can then simply calculate the diameter of the reactor. So from these simple calculations, you know the volume, you know the length, and then you know the diameter. So that's how you get your insights on the catalyst, the size of your catalytic reactor. So that's number one. So number two is that if you have you don't know the B, the yield of B, but you do have like a kinetic or expression. So you have, for example, you have reactions of A, for example, yeah, it's a minus K and then Ca to the power of 1 or 2 or 3, up to you. Just make it 1, for example, in this case, to make it easier. So in this particular case, then you can then say, for example, yeah, I want to vary this. So I want to have like an automatic calculations to say that, for example, if I have this this reactor, and then if I have another reactor like this, right? So so all is then A, and then this then B, is then B. How much is then B over here? How much is then B over here? So in this particular case, if you know, so that means it works the other way around. So you need to specify the length of the reactor, and then the diameter of the reactor, and then you put this kinetic expression into symmetry, and then you can then calculate how much then the B. Yeah. So so in this particular case, then you can use if this is like a heterogeneous catalyst, yeah, and then you can use what we know like a plug flow reactor, so PFR. So in this case, you have to specify the length of the reactor, the diameter of the reactor, and then whether or not the pressure drop is calculated based on the Ergun equation, because it's a fixed bed. And then you can also say, well, the reaction happens in the overall phase, whether it's liquid or gas, or just simply at the gas phase. So you could specify that, and then you can then say, okay, what's then the pressure drop is either you specify yourself or being calculated, and then you can then either select one of these two, either there is the
On behalf of the committee, apologize for the technical issues. We will wait a few minutes for the speaker to enter the session again. Thank you.
hello.
Yes.
I'm sorry, yeah, my computer suddenly crashed. Okay, I'm trying to open the symmetry, but now it's gone. Um, The two approaches that I mentioned before, was it clear or not clear? Now it's gone. I haven't saved it. Okay, now anyhow. Yeah, 1 minute. Yeah, was it clear or not clear? The one that I explained before. Let's use this team. Water, and then you can use semicolon. Yeah, you can use semicolon to get all the yeah, some components simultaneously. You have oxygen. Have methane, right? You have CO2. So you put semicolon in between. After that, so you have everything together, and you can just press one times, and then everything will be selected, and then press another, and then they're all there. Okay, and then done. So it's important to save your work every now and then. So you have now natural gas. Is there any questions? Any other questions while I'm doing this? Or was it clear? Was it clear previously? So I have to make it in the. Was it clear or not clear? So we have to make it.
For me, it's clear.
Probably. What does it mean by probably? 1000. This natural gas, right? Natural gas. So I put like 1. And then 1, and then okay. So natural gas, and then we have air, right? So we have air. This is for the sake of introduction. So we have now 25 degrees and now 202 bars, and then point. Okay. Clear, and then the 1000. And then we mix them, obviously, right? So mix them because we want to burn them. Right. So it's automatically solved like it was before. Okay, and then we go put it there, and then it goes to the reactor. Where was it? No, equilibrium reactor. Yeah, so if you want to use this PFR, you can if you have the kinetic, again, like I explained before, if you have the kinetic, and then you can use, and then obviously you can use this PFR, but again you need to decide on what's the length and diameter, and then it will then calculate for you what is then the outlet conditions. Yeah, so once you specify the reactions, all of this kinetic will be available. Now it is empty because we haven't specified anything. But for this simple conversion reactor, yeah. For the questionnaire, if you the person who asked this, what's his name? Her name, Surya Raj. So if you have like a specific example on this, just let me know. Yeah, you can write down the kinetics in the chat, and then we can then simply I can then simply show you how to do so. Yeah, just find that particular problem that you are concerned with, and then let's do so. So connect it over there, and then we have reactions first, and then we have methane is -1, carbon dioxide is also 1, and then we have water water is 2. So conversion is 100%, and then base component is methane. So done. So we have done the reaction. And then we know that compression is 100%, or we make sure that it's going to be 100%. And then now we specify, because as of in all fluids, it will only flow if there is a pressure drop. So that means we need to specify what is the pressure drop. So we either specify what the pressure drop is, or we just key in what is then the outlet pressure. So say, for example, it's just like a very simple reactions. So probably what 1 bar or something is then 1 bar is then 10 kilopascal. So 1 bar is then the outlet, the pressure drop. So the outlet pressure would be 190 kilopascal. Now, once we specify directions, we have specified the pressure drop. So we need to specify what is then the state of the reactor. So this reaction, it is an oxidation reaction, right? Oxidation reactions, which means it is an exothermic reaction. So it will then release heat. So that's from the reaction standpoint. But then from the reactor standpoint, are we going to operate isothermically? So it means we have a constant temperature. So if we do so, that means we can then simply specify the temperature here. It will then calculate for us how much then heat to be released, because we are releasing heat, but you want to control the temperature in such a way by having a different type of cooling medium, for example, yeah. Or we can just let the reactor behave adiabatically. So that means there is no heat going in and out of the system. So in that case, we put out Q equals to 0. So if we put Q equals to 0, this particular exothermic reactions will have its own temperature increase from 25 degrees C to 600 degrees C. Okay, 639. So this is what we call like adiabatic temperature rise. So maybe somewhere in the future you'll be asked by someone, just calculate for me the adiabatic temperature rise. So this is then how you do it using software. In my time, we have to use Excel to calculate this adiabatic temperature rise. But nonetheless, you know how to do this, yeah? So we have the reactions, we calculate how much is then, we get this data from the textbook, and then we can then calculate how much is then the adiabatic temperature rise by knowing the heat capacity of all components involved. Okay, so for example, if I don't be, it's not behaving like adiabatically, so that means I keep it like I don't know, maybe I want to maintain the temperature like 50 degrees C. So that means if I maintain temperature like 50 degrees C, that means during this combustion process I have to take that heat out. Yeah, I have to take that heat out. So how much is then the amount of heat that I'm taking out is this much. So this is what we mean by, say, for example, I want to increase steam. Yeah, just put like I want to make like produce like a 3-bar steam, for example. So I put like a 150 degrees C. So if I want to create 3-bar steam from this reactor, so if I just simply Google this, yeah, this reactor cooling. So you could see. Now, see. So now this reactor, is it easy to? Yeah. Anyhow, so this reactor, it creates the heat, and then that heat is then being used to create steam. So typically we have like a jacketed steam over here. So it's either around like a jacket or in a coil. So the amount of steam that we could create is then we have to calculate the heat enthalpy of that particular steam at that pressure, and then you use this amount of energy. Then you can calculate how much steam that you can make. Yeah. For now, just keep it adiabatic. Just keep it adiabatic. And this is it. For the time being, yeah. And then I'll show you, because we're going to need that heat. That heat is going to be used. Remember this task. So steam is then being produced. Oh, sorry, the heat is not being used, but then that particular steam is being used to heat to produce the steam. So you could do it 2 ways, yeah. In this case, you could do it 2 ways. you do what I said before. So what type of steam that you want to produce? What type of steam that you want to produce? Are you going to produce like a higher pressure steam or lower pressure steam? So say for example, you want to make like steam table. So if you go to steam table. So steam table images like that, like this. So steam table. This is steam table block. So now, say for example, pressure, temperature, right? So very good. So you have what's the unit of the P? The unit of the P. Oh, bar. So you have bar. So yeah, for example, you have like 1 bar. See, 1 bar or 1 atmosphere over here. You have like a 100 degrees C of saturated water, which is then the boiling temperature of the water. Say for example, you have this guy. Close this. So this guy, it can create up until 600 degrees C. You can see that, yeah, up until 600 degrees C. So that's 600 degree. So that's 600 degrees C. So you could then have, yeah, depending on what you want. Yeah, for example, where's that? I'll have to put that Rankine cycle again, because it has something to do with this. Well, it will have everything to do with this Rankine cycle. So you can see, because it will then create steam. So and then this steam is going to be flowing through a turbine. So the higher the pressure of the steam that you make, and then the more power that you could generate. Yeah, and the higher the pressure, and then the more it is, the more power that you can generate. So it depends on the pressure and then the amount of volume, the amount of steam that you are generating. So, but then since we have like a fixed amount of energy, and then you can then play around with what is then the pressure, what is then the flow rate, in such a way that you can then find how much is then the electricity. So it's something that you have to find. So let's assume that we make like I mentioned, like a 150, like a 5 bar steam, yeah, 4 bar steam, yeah, make 4 bar steam for the time being. 4 bar steam. So in this case, this is one approach, right? This is one approach. What I mentioned is that in this case, you you make this so you make this like a 150 degrees C, 150 degrees C. And then the steam that you can create is then, if you put like 4 bars, that means you have you need to have a temperature of about 144 something. Yeah, if it is 144 something. So maybe then you can have like a to have like a nice driving force and temperature. So 160 is good enough. Okay, so then you can make like about 4 bar steam. And then this then the amount of energy that you are releasing. And in this regard, if you put this energy, I think you can put that energy. No, no, here. No, so it doesn't. It's not being used somehow. Nonetheless, you know what the energy is, so we can then say we could use what we call process calculator. So in this case, so this process calculator is our like a control panel, so to say. So this control panel. So steam 4 bar, 4 bar, and temperature is 4 bar. And temperature is 140 something, 144 about. And then the amount of temperature in reboiler and boiler. meter or whatnot. So this is then this guy, what we specify over here. Yeah. No, we cannot do so. So what we could do is then we can make connections over here. And then what we could do, there's another trick, because we cannot make a connections. See, I cannot make a connections. So I remove this and I put it over there, 160 degrees. See, so this done now being calculated, and then you can see we can have the 160 over here, and then the energy is over there. Then we can then say, okay, now I copy connections, yeah, copy connections, yeah, and then we put it over here and then paste connections. So it is being connected, okay. So for example, if I change this to 155, this is then changed accordingly, and then the amount of energy released is this much. Copy connections. So this is, yeah, it's very ugly. Watts. So how much is this? Divided by 1E6. That's this megawatt. 0.6 megawatt. Okay, save. Don't forget to save. Desktop. This is UTP. Oh god. Okay, you can see now here. This value is connected to process control 1 PC1. This PC1 sheet 1, which is sheet 1, and then B5 over here. So this guy. Okay, and then the this one is yeah, that number. So so that's one, and then you can say, okay, this then the amount of energy release, and then you can then calculate if energy of water is about, I don't know. So for example, you can have like a 2,100 roughly kilojoule per kilogram. So that means if you have this megawatts, so this has to be like multiplied by 1,000 to get it into kilojoule, and then you divide this by this guy, and then you will have steam in kilogram per second. Can you follow? Can you follow or not? So we divided the amount of energy released by this energy of water. So this 2,100 is this what you get from the steam table. So for example, you have in average, yeah, because the heat of evaporations of water, it varies from temperature to temperature or from pressure to pressure. So the highest being around 100 degrees C or less. It's about 2,200. So in average, I would make like 2,100 kilojoule per kilogram. So this is then one way. So this is then the amounts of steam produced. So this is then the steam that is being produced if we have like a 4 bar steam somewhere. Yeah, about 4 bar steam. And then that limits the temperature of the reboiler in like about 155 or 160. So that strongly related to the how we design the heat exchanger later on, or the boiler system later on. But this is to give you an idea on how much is then steam being produced. So this is one way, okay? One way. Another way is also okay. So another way is that for example, yeah, I'll make another reactor. Just to give you an idea. We can also clone this, and then they are connected. Yeah, clone and then they are connected. So this stream is we create ports. It will then copy either the in or out port. So here out, I just copy the out ports, which is then on here. So I copy that, and then I copy this as well. Copy, and I paste it over here. Paste. So let's see if it works. should work typically. See, all of the data are there, and then directions is also there. And then we need to connect this to the other S1. So we can then see, click the drop down over here, and then S1 out. See, S1 out underscore 1. So this is then a copy of this S1 stream. And then you have this connected. So all of this input is automatically connected. And then we can see, say, for example, if I want to make this adiabatic, yeah, so I contain the heat. So it's the second way. So it will then be doing it that way. And then we have the outlet stream. And then this outlet stream, we need to use that energy, right? So because this energy, this outlet stream is 639 degrees C, 639 degrees C. So I want to use that energy to create the steam. So in that sense, we put a cooler in it. And then that cooler is, okay. Oh, I don't need to, I can directly put a heat exchanger, because then the heat exchanger. So heat exchanger. And then I have to have a stream, right? So water stream, because I want to make it a steam. And then this is obviously like 25 degrees C. It's also like I don't know. So this is then depending on the bar and the bar on the pressure. So say for example, this is option 1. Water pressure. Pressure, the same, steam pressure. Steam. So in this case, it's a 4 bar. Put it over there. And this is then 4 times, because it's in bar 1. And then this is then we can connect these two copy connections and paste connections over there. Yeah. I copy this simply because I just want to change this number, but you could also make this independent. It's all up to you. But nonetheless, I want to make these two options are comparable. And then in this case we can say, I don't know, it says here like a kilogram per second. So I put like, this is then 1,600. So I have that kilogram per hour. So it's about 1,000. So let's say 1,000 as well. 1,000 as well. And then this is then pure water. Okay. Yeah. Okay. So I have this, and then this is then connected to that particular heat exchanger. And then obviously in this case, we have to, it helps you a little bit on what is missing. So pressure drop always, because if there is no pressure drop, no fluids can flow. So it makes like 20 kilopascal for both. And then the outlet temperature. So here we can say, we can use the same number, as in this case, temperature is that guy, and then this is then being used to this guy, right? The copy connections, outlet temperature. No, there's no outlet temperature. Outlet to. So that means then I have to use the same approach. So that means I have to have this guy. I copy connection, right? Connections. Skill. This connection. Copy connection. Paste connection. Sorry. But now it's all once we know the temperature outlet over here, that means it will then calculate how much then the Q, and then that Q is then going to be used to heat this this water stream. So this part of the pot is calculated already, like you see. It's calculated already, and just a matter of us connecting the. So this is then the steam being used. So that steam being used is S5. So S5 is in this case yeah, it's 1000, right? And then the temperature is about 141 degrees C, 141 degrees C. Yeah. So this is our approximation. Is not that very accurate. So 144, but then this then 141 degrees C is the one that is more accurate. So yeah. But this is related to the to this particular design, yeah, to this particular design. So we have this 1000 inlet, and then we have to and then we have everything. I think about the same. It's just a matter that we have the enthalpy of this particular steam. We use it use it different, so it's not 2100. So it's something that is more accurate regarding related to this pressure and temperature. So this is then your steam, yeah. So this is then your steam. So I've now shown you two ways of creating steam. Okay, steam is steam produced, and it's basically your input. You know, this guy is basically the input, but nonetheless, just copy this. For the sake of completeness, this is then temperature. And then the vapor fractions, somehow it is not fully vaporized yet, so we need more energy. We need more energy, or we can then use a lower steam flow rate. So in this particular case, we can. So I'll make it. Okay, steam. So we need to make sure that this is 100%. So steam fractions, steam wetness of fraction. Okay, something that we can connect over here. So we want to make it like a dry steam. So what we have calculated above with this approach, with this approach is we don't know how much is then. We don't know whether this steam is then is dry or not. But with this second approach, we know that the steam is wet. So what we could do is that we can either put more natural gas, yeah, to give us more heat, or reduce the boiler feed water to increase this. So which way is up to you. Okay. So now in this particular case, well, if I have more natural gas, that means I could do a lot more. But one more thing to consider is that these combustions, we assume it to be like 100% combustions. So that means I need to make sure, practically speaking, the concentrations of air, the concentration of oxygen, the concentration of oxygen at the outlet of the reactor at the flare tip has to be oxygen has to be like 3%, 2 or 3%, 2 to 3%. So this concentration has to be 2 to 3%. We are not enough. See, this is not enough. So we still have a lot more. See, we still have a lot more methane not burnt. So I'll open for you the reactor itself. So we have so oxygen is consumed in the out, and then sorry, flow rate for mole flow. So oxygen is consumed, but then the methane is not consumed completely. So we need to increase the amount of air in such a way that we can then increase it a bit. We can consume the methane a bit more. So what we could do in this particular case, we fix this because this is still not consumed, and then this is consumed completely the air. So we need to increase the air flow rate, right? So now complete combustion. So oxygen mole has to be, yeah, let's make it required. Oxygen right, is then 2.5, right? 2.0. which is here, it should be 0.025. And then what is this then? This is the mole fraction is 0. So I copy this, and then this is then what I have to paste. Okay. Doesn't want to be copied. Oh, another expansion. Copy. This is calculated. So that's the error. Is this guy? Okay. So in this case, we want to minimize this. So we minimize this in such a way that we increase the air flow rate, right? So if we minimize this, that means this guy becomes closer and closer to 2.5%. So how do we do that? We either make it like a manual like this. So I increase now. So I increase now 2000. We have the temperature cross in here. The temperature cross in this heat exchanger, so something that we have to be careful about. But we still need to. We will look into this later on. Yeah, we'll look into this later on. But we are not getting any better. So and then we could also make like 10,000. So we're also not getting any better in this reactor. So indeed, we will have to reduce the. We have a reduction in the methane. So it was 58 something, now it's 25. So we are getting somewhere. So we can do controller to adjust it automatically. So I want to say, so I want to have this error becomes 0. So I copy connections, put it over here. So I want to have this error becomes 0. Yeah. The target is obviously 0. Okay, target is obviously 0. And then what do I manipulate? So if the target is 0, what do I manipulate? So what I manipulate is then the flow rate of the air. So in this case, this guy, copy connections and then put it over there. And then it means is the step size. So you can put like I don't know. So now the target is 0.05, so it's not yet okay. So we want to have it like it's 1.9, so it's less than 2.5%. So you want to make it you can increase this a little bit more. I don't know. Maybe you can increase maximum error to become like either one of these. There. So maximum absolute error I increase, I reduce the absolute error, so that will then create this guy. So in that sense, we need to have 19 tons of air, 19 tons of air, as opposed to 1 tons of air previously in the original case. Okay, so that's we solve it. So we have a complete combustion criteria fulfilled, and then now we have to solve what is then happening. We'll have to make this like that, so make it nicer. So I want to make it like how do you call it? There's a temperature cross. So what is happening? Temperature cross. So we have for example, in this case. So we have the adiabatic temperature rise of this stream is about 1700. It was 600, now 1700, much high. And then we want to reduce it to 160 degrees C. Yeah, and then by doing so, we are increasing. We are using the steam, which is then we use 1000, and then. Because we are increasing now the amount of energy, that means this flow rate of water is too small. Because it is too small, its temperature goes to thousands of degrees C, which is not correct. So we could do the same way, like in this case. So we could also do that that way. Or yeah, this one we have to be very careful. We can increase the flow rate of steam. Yeah, we can increase the flow rate of steam in this regard. So Yeah, I can increase this to, for example, we increase the energy by from 1,000, the natural gas. Sorry, how much was it? Don't remember. Oh, from how much was that? I don't remember now. It's to 11 megawatts. So we increase it like maybe 10 volts, maybe. Yeah. So now if I put like 10,000, what's going to happen? So if it's like 10,000, it is still okay. But then the temperature of the steam, it's 881, which is, yeah, it's too much. So we want to make it like about, I don't know, maybe about 300 or something. So we increase it to 15,000. Now that's about correct. To 10,000. Yeah, it's about that number. So how do I know? You go to Steam table and then you figure out, okay, the about. So about if the temperature of the steam is about like 3,300 something, that means 300 something is somewhere here. 234, 35 is somewhere here. So your pressure is about 100 bar, 137 bar. 137 bar, 35, 135 bar. So it's a very huge number already. Yeah, you could increase this a bit further, and then if you increase this a little bit further, that means you will then have to reduce the steam. So it's something that you could do. Yeah, this one I think we can make it. So instead of having this, I would want to give this as a controller. So I want to control this 14,000. So in this case, I disconnect, and then I connect this to the input, which is this guy. Copy connections, and then put it there. So this is as an input. Okay. Yeah. So now we have okay. So now we have 400 kilopascal of pressure. So we could do so. So if I want to increase now, so instead of 400 kilopascal, I want to have this also controlled. Yeah, I want to. So I have to. I will then have to remove these connections, disconnect, and then add somewhere here. So this is then 4 bars. This times 100 kilopascal. This is then connected to the stream. Okay. Okay, now. Okay, so we are aiming about this 330 something degrees here. And then if we increase the pressure, 1 minute, yeah, how do I pressure? Connections. Oh, this is the pressure. So I put it this bold. Yeah. So if I want to increase the pressure, for example, in this case 137 bar, right? So if I want to make like 137 bar, so it's about the steam produces about 400 degrees C. For the exchange, yeah. Yeah. Where's this stuff? At 400 degrees C, I increase the steam pressure 400 degrees C. 400 degrees C, and then the flow rate is that number. Yeah, it's about that. Yeah. Okay. Okay. Now, this is the amount of steam that we can produce. Yeah, that we are producing with this setup. And then what do we do? Is there any questions? Because I'm now doing this myself, and I'm feels like I'm losing you, or you are losing me. Right. Now. How do I make this? Let's leave it. Okay. Now this may looks complicated, but it may look complicated, but well, I'm just showing you all the possibilities. It's all up to you to pick which one is then okay that you want to follow. 1 minute, yeah. So we have the steam. Now we have the steam, which is over here, and then this steam is then going to be sent to a steam turbine. So this steam turbine. There is the third way, yeah. There's the third way, and then where we make the cycle first, and then we do walk around it. So I will okay, let's do so. Let's do so. Let's see. That's another way. So this is the first way, second way, and then there's the third way, which is the easiest one, which I just realized. So we now expand this to a turbine, right? This steam to a turbine. So we expand it, and then we expand it to, like, I don't know, for example, a condenser, and then where we have to have like a water or air. So in this particular case, we can then drop it down to atmospheric, for example. So we have atmospheric. Atmospheric is then, so let's put like 150 kilopascal. And then the efficiency is about, let's put efficiency is about 85%, and then you can see now we can see the energy. We can get the energy out, which is in this particular case 2 megawatt, 2.8 megawatt, right? So I copied this. I copy the 2.8 megawatt, 2.8 megawatt, copy connections, and then put it. Where's that guy? Put it over here. Turbine efficiency. Point 0.85 megawatt, and then this is then the efficiency is, yeah, I need to have, it's not that easy, yeah. I need to have like pressure out. Not nice, because these two, pressure out and turbine efficiency, is the input, so we need to make it copy. No, I'll do later. Okay. And then we have now the stream. Oh, 50 degrees C. So again, we use the same trick because we want to copy that number. So I delete that over here, put it over there, and then I copy this kilopascal. I increase this to 200. So we would expect the electric power would then drop by a certain number. So it drops to 2.7 instead of 2.8. 2.8. 2.8, 2.7. So we can play around, yeah. So you have like a much more efficient turbine, then we can have a higher C3, a higher or a lower efficiency. So that is one way, and then now we have this turbine. So let's complete the cycle. What do we have next? And then it's a cool bag. So we have the turbine. So we have done this, we have done that, and then we are cooling it down. We're cooling it down. What's temperature over here? So to know this temperature over there, you can either hover over it or double click on that, or you can have like a show PFD data sheet. One minute, yeah. At 11:30, we'll answer some questions. For the completeness, I don't want to have this. Put it over there. So mass flow temperature, yeah, I want to have no comma there. Yeah, I don't. Now you have. So temperature is about 111. So 111. So we are typically cooling it down with air or cooling water. So we cool it down to, for example, in this case, rotate that one to make it nice. So so we cool it down to, yeah, maybe 60 degrees C, right? Pressure drop is 1.2, 0.3, 0.2, 0.2, 20 kilopascal. That one, and then you have your and then cooled stream. So it's purple. So that means this purple is fully liquid. And then once we cool it down, we pump it again. So we pump it again. So we have a nice pump operating only at like 60 degrees C. And then they switch it the other way around, put it over there. And then I have the pump is again efficiency is about, I don't know, 70% maybe. And then the outlet pressure, because now we want to have now that's the trick. So we want to have a pressure of about 137 bar. So we need to have 137 bar, 137 bar. That's one. So we are pressurizing it to 137 bars, and then we are connecting this to that guy. We're simply now connecting this to this heat exchanger. Yeah, we're connecting this to that heat exchanger. So save it first. Now let me think on how to better do this, because let's see. This is what we have from this stream is simply steam pressure is that guy, which we can then copy later on, and then see. So this input is basically, so 137 is, we can take it from here, and then this is then also there. So what we could do is so now we can make a copy, or I'm not very sure if copying this would be that easy. Now I will take this out. Okay, it is all locked, so I unlock this and then take that out, and then make this guy over there, and then okay. So now 137 is okay. 137. So this is option 3. We make the cycle now. Steam pressure, just copy this guy. this. This is bold. Okay. So I put over there. These connections. So I have the pressure out, and then the steam produced is steam 1,400, 14,000. It is. To this guy, you know, same then to this guy, base connections. Okay, right. So it's all water. All water. Yeah. Okay. Now. So now we have this stream, and this stream is going to be connected to that stream. So in symmetry, if we do it right, so we don't need to identify any recycle stream on this cycle if we do it right. So let's see if I do it right. Otherwise, we'll have to identify one of the streams becomes a recycle, which is most probably this stream. So apparently we do it right. So in this particular case, where is that stuff? I want to have this queue. Show right, in unit is in megawatt. So this is the amount of energy that we are using, and then this is the amount of energy that is being fed in. Copy that add to POD data sheets. Add to POD data sheets. Come on, add to POD data sheets. Oh, we have it already. Sorry. Config. Delete. This is in megawatt as well. Yeah. So see that we have energy coming from this burning of the methane. It's about 11 megawatts, and then the amount of energy that the amount of electricity that we produce is about 2.9 megawatts. So that's very inefficient. So what you could do, because there's so many inefficiencies over here, so we have inefficiencies in the pump, which is then 70%. So you could also extract this out. Yeah, you could also extract this out. Extract this out. Turbine efficiency, pump efficiency. Down. Copy. So if you put this 70, so if you increase this to 80, see what happens in the energy stream. So it's not so much of reducing, of increasing this, but it will then reduce this duty a lot. So for example, in this case, how much is the energy removed? Yeah, how much is the energy removed? Because the energy has to be balanced. 1 minute. Heat in, energy in. So we have burner. We have pump electricity. Yes. Burner is this guy. Copy connections. So this is what. This is thermal energy. Yeah, you have to make sure that this is what is thermal energy. And then we have also electricity from here. This is electricity, not thermal energy. So the watts, even though they are the same watts, but they are completely different. What's electricity? Create thermal to create electricity from thermal. There is a huge efficiency loss as well. But nonetheless, if we assume 100% efficiency in this case, we have a total energy in watt. So you can see the electricity is not that much compared to the burner. So so energy out of electricity produced. We have condenser. So in this particular case, energy produced is this guy. Yeah, you could copy this, copy connections. So you have watt as well. And then sorry, disconnect. Copy, paste. And then this is then the condenser. Copy, paste. Okay, now you have a balance. So you have a balance system now. You have a balance system. And then you can say, okay, now the efficiency of this cycle highly depending on how much is then, because the goal is then to create electricity from the energy. So you can see much of this energy, 11.8 megawatt, it goes to this condenser. It goes to this condenser. About 9 megawatt, it goes to the condenser. So efficiency system, I can. Then the amount of energy that you produce, this one, sorry, this one, energy produced divided by the amount of heat that you have in, or basically that one. Or maybe, yeah, it could make both of them, yeah, because this is also energy that you need to pay. So you could do this or that one. So yeah, up to you. So in this case, this compared to. So it's about 24%. So it's about 24%. So now you can, hey, okay, now if I want to play, if I increase this to, if I put this to 130 bar, what happens? So you are reducing the efficiency of the Rankine. So now you can play around. Now if I put like steam pressure, this is your efficiency. So you can make now 130, sorry, this is 4. 4 is then 14,000, all right? Can make a nice table, yeah. So this is then the 24.4%, and then if we have like 150 bar, so 150 bar, just to make it 14,000, and then you have like a 25%. So if you increase the pressure, your efficiency gets increased, and then you can have like a 170. So 170, and then this is then 25.6%. You could also do like I want to make like a 200, 190. Up to you, yeah. I mean, this is then something that we can play around. And you could also make like, for example, yeah, 190. So if I want to reduce this to but be careful, yeah. If we reduce this number, there will be like a temperature cross over here. So we need to make sure when this is then, sorry. So the steam produced temperature is now 500 degrees C. Copy connections. Temperature. And you can play around. Max is, if we say that max is then 350 degrees C, that means this is something that you cannot allow. Okay. So in this particular case, for example, let's go back to 130 degrees C. 130 degrees C, okay. it's also not so much. 130 degree C, that means you have to increase this to, I don't know, to 15,000. What was it? How much was that again? There, the 19. Okay. Sorry, 19, 18. Right, yeah. No, 16 and a half. Yeah, somewhere around this number, yeah, somewhere around this number. But you need to make it consistent. So this then 16 and a half. And this is then to 2.5% to this is as well 16 and a half, and then you make it 150 degrees C. But this is no longer acceptable, so that means you have to reduce it. You have to, sorry, reduce it. You have to increase it. Somewhere around this, right? You have to, but you have to make it consistent, yeah. Maybe if I want to make it, yeah, somewhere around this, 17,200. Efficiency is then 22.7%. So there is some very increment value. And then you increase to 70 bar, and then you have to increase this as well to how much is that? 18,000. Yeah, something like this, 18,200. 2.7%. So if we increase the pressure, but we also increase the if we increase the pressure, but we also increase the flow rate, that means the amount of energy is about the same. Hence, the efficiency is also about the same. But then, because this is limited by the maximum temperature that we apply. So if you don't have any limit on this maximum temperature, as you saw before, you could increase this efficiency a lot more. So that's the thing that you can play around. So you could also play, for example, the pressure out. Yeah, the pressure out. This is the pressure. This pressure out, but also like dropping down, and then you can see how much is then the efficiency can be increased. So I think with this, I'm not really sure if you can follow me, but nonetheless, and it's all like blah blah blah, so blah blah blah. The aim is to produce 220 megawatts. So now, if you know that you have to produce 220, this is the how much is this? How much is this? It's only like 2.8 megawatts, 2.8 megawatts. So that means you have to increase the size. Yeah, you have to increase the size. So what's the size? Yeah, the size is then the amount of because all of this electricity is coming from this burning of the fuel. So that means you have to increase the amount of natural gas that you need to or fossil fuel that you need to make. But this is by no means is a green energy, yeah, because it's all fossil. So in that steam temperature, so it can go until 700 degrees C, while in my example, it's 350 degrees C is about that maximum. So inlet steam pressure about 30 megapascal, so it's about 300 bar. So then you have now 170 bar. So now you can play around until 700 degrees C and then 300 bars. Yeah. Low sulfur grade coal as source of fuel. Even use coal. Okay, it's even less green and less green. It's dark black. Photon to yeah, I don't know what it means. So it has to be something related to the efficiency of the turbine. It has to be something related to the efficiency of turbine, I guess. Yeah, high-tech turbine. So find out what the efficiency is using this number. And then the cooling medium, it's all up to you. So this cooling medium, it really depends on how much you want to cool it down. So if it's for air on water, 600 degrees C is the correct way. So that means if you use like a refrigerant, that means you have to cool it down. You can cool it down a little bit more further, but then to make this refrigerant, you have to create another cost. You have to put another energy, so it will then add up to the amount of energy coming in. Okay. So I think I will stop here and see if there is any questions. I'm not sure, Arisha, if you can let me know if you can or cannot follow me. Yeah, because I was like playing for myself. Um, I'm rushing. So any questions? No questions? Hello.
Hello, Mr. Zulfan.
Yeah.
Actually,
Oh,
we have one question at the beginning of the session, which is from from Nalakula Sirisha. She asked whether the symmetry can be used for desalination purpose.
you can do it with everything that you can think of.
Okay.
Because basically it's all tools. If you know the most important thing to know is then the functions that are what that process is all about, like these desalinations. What is the process all about? Like I showed you what this Rankine cycle all about, and then from that process, we then derive what type of functions that we need to have. So, for example, in this case, where's my in this case, your Rankine cycle, we need to have something that burns the fuel. Hence, we make it. Hence, we make this. Sorry. Hence, we make this. Yeah. Hence, we make this, and then this. What do we burn? We have the fossil fuel. In this case, I put natural gas, and then we have to have air, and then we define the reactions, and then we extract the energy. So that's this reboiler. So the whole thing over here with all of the controllers on the air burner is then the boiler basically. So this whole thing is boiler, and then the steam is then this whole line. So it gets steam. The steam goes to the turbine, and then it goes to the condenser, and then it goes to the pump, and then goes back to the boiler. So this is how you saw it already. How we model this. So understand the process is very important, very crucial. If we understand it wrong, that means we will then model it wrong, obviously. And then second one is that we know what functions are needed for such a system, for such cycle. Yeah, but in short answer, if you say can we or can we not, it's always we can. Yeah, yes we can. Or Malaysia boleh. Um, um, this one I don't know. I don't know. I don't know. This one I think we have answered. This one. So Surya Raj, do you have an example? Now we have some more minutes to questions. Do you have an examples on this? So then we can just simply play around and plug it in so that you can. Because if I only explain this, yeah, maybe you understand it, maybe not. So it's going to be very difficult then if you want to do it yourself. So you have a specific example, then just ask me and then we can do it now. Okay. I don't have the kinetics at all. Yeah? If you don't have the kinetics, then it's a pity. So steam methane reformer is a very well-known process. So you could easily Google this and then find the kinetics, yeah, with whatever catalyst. So you can easily find it. If you don't, that means you have to make an assumption. So yeah, and then I don't know why you need to have a specific nickel-based catalyst, or is this the only catalyst? So this is something that I don't know as well. So yeah, so yeah. Ja, steam methane reformer. Yeah, you have it. Huh? It's not that difficult, right? So kinetics. All mass balance, energy balance. They have the kinetics. If they don't, that means then you have to oh no, they have the kinetics. CH4. So we only have in this static example we just get this. So it's quite complicated kinetics. What is this W? Pseudo contact time, residence time. Okay. Yeah, residence time is easy to calculate. So what is then A1, A2, and A3? Something that we have to take. It's very easy. Yeah, ration parameters. What is the equation here? This one. So A1, A2, and A3. A1, A2, and A3. Oh, mom. Because we need to have the kinetics in terms of that K, and then in terms of this. Oh, okay. Okay, this one. What is this? Unit less term. Unit less term. What kind of term? Oh, this term. Wait. Yeah. You have the kinetics. So in this case, K. What is K? Yeah. Oh, KCO. KCO is K1 in Roman. Oh, this one. K1 is this one. K2 is that one. K3 is this multiplied by that, and this guy is over here. And then we just need to know what is then KCO, KP, KH2. And then this KJ is KOJ. So we need to find KOJ and then EJ and IG. And then this whole KCO, KH2. Oh, KCO, KH2, I guess this is then the KJ and so on. Oh, this one, KI, bigger K. So where are the numbers? The numbers. Where's the number? Yeah. See, this is the difficulty. What is this? K0. Complicated papers. It gives the kinetic expressions, but there is no numbers. Right. What is this? Yeah. Anyhow, you have to go through the papers. Kinetics. You can also do this for simple kinetics. Or you could also find somewhere in the textbooks, yeah. You have to find the paper, find this paper, and then the paper. No. Oh, it's different. It's a different base, but anyhow, because this base is I think alumina, rhodium. This one is alumina. This is rhodium as well. So, yeah. Anyhow, any other questions?
Hello, Mr. Zulfan.
Yeah.
Here, I would like to take the opportunity to ask a question from the audience that has been sent through the registration form. The question is symmetry useful for fields other than engineering as well? If yes, can you please explain for which fields and how so?
Say it again. Sorry. Say it again.
Is symmetry useful for fields other than engineering as well? If yes, can you please explain for which? Apa?
Say it again. Use what? His symmetry is using what?
Is symmetry useful? Useful for fields.
Useful.
Yes, useful for fields other than engineering.
Or useful for fields other than engineering.
Yes.
No, then we have to specify what do they mean by other than engineering. If you go for finance, obviously it does not work for finance. I mean, if it's like HR, I don't think you will use symmetry for HR system. So I don't know what the goal of this question really is, because symmetry is a process simulation software. Hello.
Yes, we can hear you.
And then in that definition, it means even only process engineers use symmetry or HISIS or plus. There's no other engineering discipline. Even you cannot ask your colleague from civil engineering to use this software. It's impossible. So I don't know. Maybe we need to ask the question again to clarify what does it mean with the. I mean, maybe there's something in the question that we don't know. Hello.
Yes.
Okay. I don't know if that's clear. Is that clear?
Yes, it's clear.
Is there any other questions?
I think there is a question from Teo Ji Yin. He said that what are the advantages and disadvantages of symmetry compared to other process simulation software such as Aspen HISIS?
We did that already, no? Wait, where did I put that slide? I think we did that already. Let's open my slides. There are a few different things, yeah, but one minute. So the same people that developed HISIS, they developed symmetry. Once HISIS was bought, or Hypotech was bought by AspenTech at the time. So if you can use HISIS, you can use symmetry. But then since these people are the core people, so they keep on developing, especially the thermodynamic model. So HISIS has no further development in the thermodynamic model, but then so symmetry has that. So it has more elaborate thermodynamic model. So now you can model more systems with symmetry compared to HISIS. That's some of these things. And then with symmetry now you can streamline this software with because it's under Schlumberger, so you can then basically model theoretically from the reservoir up to the well, and then all of the pipelines to the top side, and then to downstream refineries and petrochemicals if you want, and up until flare. So all of these you can theoretically model them. And then you have a lot more optimization software. So this is only those of you who final year students or master students that do process optimization can appreciate this. So if you go to tools and you have optimizer. So in this particular case, we don't have time to do this, but you can do, like, for example, if you want to maximize the energy in this case, you can have it as an objective functions, and then you have a manipulated variables. So these manipulated variables is basically the ones that we put in, right? So in this particular case, for example, we have turbine efficiency, pump efficiencies, and then we have the steam pressure, steam produced, and so on and so forth, in such a way that it will then tell us what are and also the constraints. Yeah, what are then the optimum numbers for these bold items in such a way that we can maximize the electricity produced. So there are some, if you run this, there are some, where's that stuff? Settings. So there are a bunch of optimizer solvers. So as opposed to HYSYS, which is only like a 3 or 4, and then from which you can select from. So this is a lot more options. Yeah, this is compared to HYSYS and Aspen Plus. So you have a lot more options for the optimization solvers. And then this is what I like a lot now. So it has this machine learning features in it. So I think I showed you at the beginning of this, which Aspen doesn't have it, even though they claim to have it. But so in this case, example, yeah. So in this case, as you can see, so you can see swap. So you can see I make a neural network model from experiments or from other simulations, and then put that neural network model into this unit operations. So this is then going to be like a hybrid of modeling. So this is predicting something that is not conventionally predicted in the first principle model. So in this case, I'm predicting erosion rate. So if I have like a well or pipeline simulation model as a first principle, and I can put this unit operation so that I can then see how much is then the erosion rate at every elbow. So this is the hybrid simulation. So which Symmetry is now having. So another example is that this is what I meant. I said to you as well already. So you can replace the whole plant, this plant, with one block, and that's easy to converge. So in this case, because we deploy this on the plant, and then we get data from the plant on hourly basis. Some of these data are very, some of the data it cannot converge the simulation because there are 5 recycles in it, so we have to manually key in the new starting point so that it can converge. But on the site, nobody can do that. Yeah. So so to make sure that we remove this convergence issue, we replace this whole bunch of unit operations with this one simple block. So using the same input that they have, we can then calculate the performance of the unit, basically. Okay. So these whole features. So in this case, I also replace the distillation column with the machine learning model, with the neural network machine learning model. So this column replaced with that column replaced with this. So I can then visualize, I can make the plant using first principle model connect to the machine learning models, which is a hybrid, and one is much easier to converge compared to this one. So when we want to do like a process optimization, we can better use this type of modeling approach as opposed to this approach. Let me know if this is not clear. What else? Yeah, I think there are many details, but these are the big things that I think is a plus from the Symmetry. Obviously, there's also like a minus. So if you go here, I think I mentioned this as well. So I need to be able to customize my thermodynamic model. So I could do that freely in Aspen Plus, but I couldn't do so very freely in Symmetry. But indeed, the thermodynamic models are continuously updated as opposed to the ones that we have in Aspen. And then there is no shortcut distillation in Symmetry. We have a shortcut distillation calculation in HYSYS and Aspen Plus. So while it's not necessary, but sometimes we need that. And also, we can make our own unit operation in Symmetry, but it is not as easy as if we were to do it in Aspen Plus using Aspen Custom Modeler. So there's also things that I don't like from this Symmetry. And then historically, HYSYS and Symmetry, they are built for oil and gas industries. Features for chemical industries like this residue curve map, ternary diagram, isotope finder, which are very chemical industry specific, which are well, but Aspen Plus, it is not there in Symmetry. And then you will need to pay a lot more. I mean, for extra cost for network piping and so on and so forth. And there's a bug in pinch analysis tools. That doesn't mean that I like the ones that we have in the HISP and HISIS. I also don't like it. But then, well, we do pinch analysis using Excel anyhow. And then help file is not that very detailed sometimes. So yeah. Anything else? Is that clear? I mean, you can ask for more, yeah, if you think that is not so clear. I think this is so. Kong Li Jing, what do you mean by this question?
Hello, sir. Actually, there's the question being asked by the participant.
Yeah.
So I just write down.
Oh, okay. But is the participant is still here so that he or she can ask this? Because I don't understand this question. I mean, what does it mean? I don't know what it means. Because it is process simulation software. It's the same thing as saying that yeah, I don't know. Anyhow, if that participant is still here, maybe that he or she can explain what this question means, because I don't know. Maybe there is something behind this question which I don't know. And this one, I think I've mentioned this, yeah, TOG Yin. If you I mean, if you'd like to know more, just let me know. Ask me more questions on this. Is what I've explained to you. Is that does it make sense to you, or is that you need some more explanation? So whatnot. Can symmetry be this? Yeah. If you ask me again, I think this is the same questions, no? Alakukala. Sirisha. The same. So if you ask me like, can you or can you not? Yes, we can. Like Obama said, and also Malaysia boleh. It's just a matter of that. Number one, you have to understand the process. Number two is that you need to know the functions used in the process. Like I mentioned like I explained in the example that we have already. So say for example, how do we model a burner? So in this particular case, the easiest way to model a burner is this. So the reactor, a mixer with the natural gas and air, and then we burn it, and then we put the kinetics, and then we take the heat out. So basically, this is a burner. But is there any burner icon here? There is no such thing as a burner icon. So understanding what the functions really is, that's very crucial and important. So it's not only related to symmetry, it is for all kinds of software, So don't get me wrong there. Can symmetry be used for air energy storage? Yeah, like I say, yeah. If the question is about can we not, the answer would be yes, we can, and Malaysia boleh. So yeah. So again, you need to understand. Number one, you need to make a flow diagram of this system. So this system, make a flow diagram of these systems. Energy storage systems. If you can make a flow diagram for that and then share it here, and then we can do it in the next 10 minutes or so. Make the flow diagram and then the list of functions that are related in each of the block diagram, and then we can then make the model accordingly. Like MATLAB Simulink is used, yeah, exactly. So to use Simulink or MATLAB, you need to know what the system looks like, and then from that systems, you write the equations, right? So if you have the equations, that means you if you have the equations, you understand the equations. That means you know what the function really is, and then we can then model that in symmetry. I'm not very familiar with these energy storage systems, but then if you have the flow diagram, then we can simply model it easily. Yeah. How to simulate batch process through symmetry? This is about dynamic simulation, Lo Jia Cheng. So that means what we what you guys typically use is then the steady state. Like in this case, it's a steady state. So if you run this today or tomorrow, or the results will be the same. But if it's in dynamic, so the exchange is then fouling. So some of the equipments are deteriorating, and then if you want to introduce, for example, I want to fail this pump or fail this compressor, that you could do so. And then the same goes with the dynamics. So in dynamic system, you have the equipment, and then you have all the valves around it. And then when you say click start, you make the event. Yeah, you make the event. You click start, and then you can then see what is happening. I think I need to lead you to my YouTube channel. I don't know if you know it. Go here, because I've been sharing about the whole process simulation stuff in Symmetry and analytics. So you have a process simulation using Symmetry in this case. So so you go here. Well, it's in Bahasa Indonesia, nonetheless. But you could, I think you can get the idea. So there are plenty of this session, and some of this session is about dynamic simulation. I think it's somewhere 5. Yeah, 5. So this 5 is about dynamic simulation. So I think 4 or 5 is about dynamic simulation. So you can then you go here. How do I share? Can share. Share. And there's also, I think there's also like yeah, some of these are in Bahasa Indonesia, and then some of that in English. But you can, I think you can find your way. Hopefully, if not, then you can ask me, yeah, on how to do dynamic simulation, and then we can have another session if you want. But it's all about dynamic simulations. Any other questions? Here's compare. Yeah. So you have a compressor, you have a compressor, right? So you have the expander. So you saw already the expander, and compressor is just the other way around. So you could model that, and then this recuperator. So what does it mean by recuperator? So I need to Google this myself. This one I don't know. And then so you need to understand what this means. So after cooler, all of these coolers is basically a cooler, right? You know this. So it's basically this cooler, and then you have we have compressors, and then we have a compressors over here. Compressors. Here we use expander. You have expander as well. So you have the expander, and then this is then to generate motor. Yeah. So you need to understand how they work. Yeah. From here to there, you need to understand how this thing work. You have to understand how this thing works. So are they then generating power from here? So that means the same way as we are generating power over here. Is that what it means? So it's something that we have to understand first, and then if that is then the case, so that problem is solved. And you have also combustion chamber. So that means you have a flue gas. What does it mean? So what's flowing here? Sohail, what is flowing here? Is it air? Hello. Yeah. If it's air, I assume this is air. Because there is no other makeup, right? So if it's air, that means this air is then being heated and so on and so forth. So you expand it again, you heat it up, expand it again, and then it goes back here, and it's being cooled down, I guess. Yeah, because this is red, hot. This is blue, cold somehow. Yeah, let me know, because you should understand this first. And then we have this cold, and this, it goes to exhaust. So what is in the blue line? Air. So you have air inlet. Basically, we are compressing air. I cool it down, compress it again, cool it down, and then this cold air. You have this. So in this case, you have underground cavern. So in this particular case, what I assume is that you need to know what the fluctuations of or how is the system, or how much energy can we, how much is that cold air that you can store here, something like that, or in there. So depending on how much is then the flow rate of the air inlet, then you can then see how much is then the volume or mass of air, cold air compressed in here. So which you can do so. Yeah, it's very easy. Yeah. So you put the air, compress it like I showed you, and then cool it down, compress it again, cool it down, and then send it to a vessel. Send it to like an outlet stream. Yeah, that vessel is an outlet stream in steady state. Now we're talking about steady state, and then it goes to it gets heated, and then it goes out, and then this guy is like maybe air as well, like I mentioned. Yeah, Sohail, what is this? Well, if you cannot tell me what this is, then we cannot move forward. So yeah, and then this one, how is this then being connected? Right, so we need some time to understand how the system looks like, and then how the functionalities in each of the block, like I was trying to understand. So in this case, if I try to understand you correctly, if you want to see the fluctuations in this underground cavern, like here or there, so if this pressure is a lot, that means you have to send it there. If the pressure is okay or lower, then you can just simply send it in here. So in that sense, you need to model this in dynamic simulation. And then you will then see the fluctuations of the pressure in here. So it goes up and then above a certain limit, and then it has to go to this if you want. Or maybe you want to have this like a bottled air where you can just simply sell or what, I don't know. So you know this. So then you can just open this valve over here, and then you will get your bottled air. And then by opening this valve, obviously this pressure is dropping. And that means you will need to have more air, right? So let's we go with this only piece of information. That's what I can tell. So if you can tell a lot more, then we can do a lot more. Any other question? Hello?
I believe there is no more question from the audience.
No, yeah, good. In all of this, yeah, because I asked this to Li Jing, what kind of problems do you want to have? Because it will then be better to simulate this with your own problem, like what we just did. So thank you, Li Jing, for that. So now I don't know if you want to, if you can understand this quickly, but nonetheless it is there, and then you can always visit this. I will maybe share this later with you, so so that you can have an idea, and then you can then work on it, make this thing better than the one that we have now. For the other stuff, so like this desalination and then the energy storage system, is something that, again, like I mentioned repeatedly already. So understand the process first, and then understand the functionalities that are in that process. Then and only then you can model the process in any software. Yeah, not simply related to symmetry, in any software. Well, if there's no other questions, then thank you.
Thank you, Mr. Zulfa Adiputra, for the informative sharing. We may proceed with the next agenda.